All right, for the second part here, we're going to look at the atomic radius trend, and we're going to do that by looking at, or kind of explain that by looking at some electron configurations. So the first thing I want you to do is go ahead and write down those 4 electron configurations that you see on the screen. The ones for sodium, aluminum, lithium, and gallium. I have already written them out. If you don't remember how they're supposed to go, I'll walk you through that here in a second when I flip between the screen for my periodic table app. Alright, so if we start off with sodium, I had 1s2 because it's in the first row in your S block going with H and He for the first 2 electrons. So it's 1s, it's 2 because there's 2 of them, and you've got 2s, second row, S block, 2 of them, 2s2. Second row, P block, 2p, there are 6 of them, 2p6, and then 3s to the first because in the third row, and the S block is the first one. And aluminum will go the same way. You just keep going. From that, you would have 3s2 instead of that 3s1. Then you would have 3p1. If you're looking at the lithium, we would stop earlier. You would have the 1s2 for the 2 of them, and then the third electron would be 2s to the first. And then gallium, you would continue on down. You'd end up going through the 4s2 to the 3d10 to the 4p1. Okay, so the first term we're going to look at is atomic radius. Okay, and this app is really nice for the fact that it actually shows us a picture of how the atomic radius changes for all these elements. So we're going to look at the atomic radii trend like it tells you on the paper. And it says, looking across the period, what happens to the radius? So how you turn this on is you go to a little gear in the upper right, okay, and it will change the coloring. All right, and so right now it's on classification. I'm going to change that to radius, just like you did for the last paper you had to do. And now it should show us what the radiuses look like. All right, so this is a really nice picture of what these radii are. Okay, the really small ones are obviously smaller, the bigger ones are bigger. Okay, and they're measured in picometers or pm. So if I just glance across the table, okay, from left to right, you should be able to tell the basic trend is that it gets smaller. Now you notice that there are some that kind of, this one's a little bit bigger than these two. And if I actually click on all of these, if I actually go and click on another one, it'll actually change in the upper up here, and it'll actually tell you what the radius actually is. Okay, so this one is actually 136.8, whereas the one for helium is actually 30.1. But the basic overall trend is that it actually does decrease as you go across the period. Okay, you could look at the same thing if we look at a different way to represent that, okay, would be with this. This is a graph of each period. Each period, okay, is a color. And they go by atomic number on the bottom and atomic radius up the left, or up the y-axis. So, like 1 here, that would be hydrogen, 2 would be helium, then we're going to go lithium, okay, and I'll across the period, so I'm going to go lithium to neon. And then I'm going to go, this one will be sodium, which is 11, and it's going to go sodium to argon, okay, and so forth. So you can see for the most part here, you can also see how it's getting smaller. My radius is decreasing as I go across the periodic table, or left to right, okay. I'm kind of skipped some of our D block there in the middle for that one, but for the overall, we see that trend. So it's just another way to represent it versus that picture that we have there. Okay, so if I look at the configurations for sodium and aluminum, so if I go back to my worksheet here, if I look at the configurations for sodium and aluminum, notice how they both end in 3. So are all your valence electrons in an element in the same energy level? Yes, for sodium and aluminum, they're on the exact same one. They're on the 3rd level. Okay, so that's why I put yes, they're in the 3rd. Okay, right here. One's in a 3p, ends in a 3p, one's in a 3s, but they're still both in the 3rd row. So we're going to use the idea that opposites attract and figure out what might actually cause the periodic trend that we see in the periodic table. So I see that it should decrease. So we're going to try and explain why does it get smaller. Okay, well what we said earlier is that protons are positive, okay, electrons are negative. Electrons are on the outside, protons are on the inside. So it would then kind of go along with my negatives on the outside will want to be attracted to those protons in the middle. If they're attracted a whole lot, it'll be smaller. If they're attracted not a whole lot, it'll be bigger. So thinking with that line of thought, these ones here in the upper corner, okay, up here in the upper right are probably really attracted to one another, whereas the ones here over on the left side probably aren't as much. So that's what we're going to look at. Okay. Now, if I compare sodium and my aluminum, okay, you want to think about what's different. Well, what I said right up here in this problem, okay, it says sodium to aluminum. I add 2 protons, and I also add 2 electrons. But since sodium and aluminum end in the same level, they're both in a 3, okay, those electrons are the same distance away. So when we talk about 11 and 13, aluminum has 2 more protons in the middle, in the core, but in this third level, so I'm going to kind of do these as like my levels, first level, second level, third level, first level, second level, third level. So they both have their last electrons here in this third level. So I'm not gaining more levels for electrons. So now I'm trying to think, okay, well, what's going to make aluminum smaller? Well, if this has a stronger positive center, it's going to pull those negative electrons. Well, if my center is stronger, my electrons are going to feel that pull a lot more, and it's going to be a smaller size. So that's what I have written right there. Okay, the electrons are the same distance away in both sodium and aluminum. Like same distance meaning like level, I guess I should be careful. They're on the same level, or energy level. But aluminum has more protons to pull on it, so the electrons feel the pull more and actually get pulled in tighter. So be careful with my same distance away there. I really should have put same level. Sorry, so we'll just put they're on the same level. All right. So the fact that aluminum has that stronger magnetic pull is going to make it pull those electrons in that are in that same level in actually just a little bit tighter. Now if we look at our picture, okay, and I see sodium here, and I compare that to aluminum, sodium's 179, aluminum's 142, you're really not changing a whole lot, okay? But the more positives you add in a same level, okay, in this same row right here, so this third row, will get pulled tighter. So we're talking about a pull here. I have more positive protons pulling those electrons in very, very tightly. And I will say that over and over and over again, okay? So that's my period trend. Now your group trend, okay? If I look in my group trend, so if I go down the group, so if I go from beryllium to radon here, or radium, it's definitely getting much, much larger. That's really easy to tell that's getting much larger. If I go from helium, okay, here in the upper right, and I go all the way down to radon, obviously, again, it's getting a whole lot bigger, okay? Why does it get bigger? This one's actually a little bit easier, I think. This goes back to our question that we had earlier, the other question, okay, where it said, what am I adding when I go from lithium to sodium? I'm adding electrons. I'm adding protons. Okay, lithium only has 3 positives here. But lithium only has 2 levels. So since lithium has a weaker pull and less levels, it's definitely going to be smaller. Okay, the more levels you have, or energy levels you have, the bigger these shapes are going to be, the further out my electrons are going to be. Okay, so group trends are actually, I think, a little bit easier. It increases down the group, because I have a larger energy level that's used in sodium. There are bigger shapes, if that helps too. Now with anything, and this is the last thing we're going to look at for this video, you have exceptions. So we're going to talk about one of these exceptions. There are many, but there's one that kind of happens over and over again. All right, we're going to take a look at aluminum and gallium. I'll look up the radius for each one, and we're going to see if it actually follows. And since I'm telling you it's an exception, you should know that no, it doesn't follow. Okay, when I look at aluminum, its radius is 142.2 picometers. It tells me there in the little box. Okay, right here. I go down to gallium, which should be bigger, and I see, oh wait, gallium's 140. So gallium actually gets a little bit smaller. So the question becomes, what does gallium have that aluminum doesn't that makes it smaller? Well, we see all of these electrons here, or all of those D blocks, that aluminum doesn't have anything with a D block. We don't start D's till 3, okay? So gallium has all of these D block electrons, and we see that in the electron configuration, okay? Gallium has those 3 Ds. Well, they're in the third level. So gallium has its 31 positives, Okay, and it actually has 4 levels because it ends in a, I put P, ends in a 4s. Okay, so that's 4, it has 1 little electron out there, all right, but it shoved 10 more there in that 3rd level. Well, since it shoved 10 more in that 3rd level, it outweighs the fact that you're adding 1 further away or 1 level out. You're adding so many more electrons in there, okay, that gallium has such a now a stronger pull than aluminum, right? 31 positives compared to 13. So I've got 31 positives here that are really going to pull on these neutron electrons, making it just a little bit smaller in than aluminum. Okay, not a whole lot, obviously, 2 picometers, which is really, really small, okay, but it is going to make it a little bit smaller. So that's one of our big exceptions that happens kind of over and over again when we talk about things with the D block.